Hey everybody, and welcome back to Algebra 2 Online. So I thought just since we were done with the trig unit, it would be helpful to just kind of do a review video of sorts on a whole bunch of different type of trig equation, identity type problems. So this is just a bunch of things that could be helpful for the end of the trig unit here. So this first one just says, if tangent of x is -5 and x is in the fourth quadrant, find the exact values of the expression without solving for x. So you've got basically, a triangle down here. It's in the fourth quadrant, and tangent is just -5. And so, this distance down is -5, and then this distance over is just like a 1, right? Because that's how we could take the tangent of that angle, right? So we should find C because we're going to need it in order to do like sines and cosines and stuff. So C squared is just 1 squared plus -5 squared. So C squared is 1 plus 25 or 26. And really, there would be a plus or minus square root of 26, but since we're doing distance, it's just square root of 26, right? And then now you can just use trig identities to get the answer. So sine of 2x is 2 sine x cos x. And so I'll just plug in what sine is. Sine is, of this angle is -5 over c. Right? So sine is, what did I just say, -5 over square root of 26. Cosine is adjacent, 1 over square root of 26. 1 over square root of 26. And then you just multiply all that out. It's like, what, -10 over 26, which, if you want to simplify it, it could simplify to -5 over 13. For cosine 2x, there are 3 choices of trig identities here you could use, but for whatever reason, the one I always seem to remember is cosine squared x minus sine squared x. That's just the one that sticks in my brain. Cosine, like I have it up above, is 1 over square root of 26. Sine is -5 over 26, right? Oh, squared. So that's like a 1 over 26 minus 25 over 26. And 1 minus 25 is -24 over 26. And I guess that would also simplify to -12 over 13 if you want to. And so last but not least, tangent. If you do the trig identity, tangent of x equals this. And that one I always have a hard time remembering. I find I drop the 2 a lot, but just go look it up. You're not really expected to memorize any of these. You just look them up. You have a reference sheet for that sort of stuff. Tangent is -5 over 1. I mean, it's also up here. It's just -5. And then so I'm just plugging in everything I know, and then I just simplify it. That's -10 over 1 minus 25, so -10 over -24, which is, what is that? That's just 5 over 12. And there you go. So without ever even knowing the angle, right, we know the sine 2x of that angle, cosine 2x, and tangent of 2x. All right, so this is just a trig equation, and it's definitely kind of a tricky one. There's another video I had where I did kind of a 3 theta kind of thing, and they're a little weird to deal with, so I want to do another one. So cosine 3 theta is, of course, -2 root 2 over 2. And basically to do these, you have to do like a u sub thing. So I'm already using theta. So let u equal 3 theta, okay? So what I am going to solve is cosine of u equals -root 2 over 2. And then basically I'm just thinking that all students take calc thing. And since cosine is negative, right, you can't be in that quadrant or that quadrant, 1 or 4. So you're in 2 and you're in 3. And then basically you just need to do the finger trick to get square root of 2 over 2. I'm just thinking square root of fingers above for cosine over 2. And so you can see it kind of has to be like a pi over 4. So there's like a pi over 4 reference angle here and here, right? If you think quarters, right, this is 1 quarter, 2 quarter, 3 quarter, 4 quarters. So that's 3 pi over 4s, right? And then you go 1 more pi over 4, you'd be at 5 pi over 4. So U is basically either, what did I just say, 3 pi over 4, or U is 5 pi over 4. And then you just unsubstitute. So, 3 theta equals 3 pi over 4, or 3 theta equals 5 pi over 4. But you should be careful, and I'm going to do this in a different color. So we are only concerned with the solutions between 0 and 2 pi, but because we're chopping it up into 3 in a second, we're going to divide by 3, we chop, there's always this plus 2 pi n in these problems, and we're going to chop that up into 3 also. And so it could change, and it will change, how many solutions we get in one full circle. So you'll see what I mean here. So if I divide by 3, right, here, and I divide by 3 here, I basically would have, struggling on what color I want. So this one's kind of nice because if you divide by 3, the 3 here cancels. So you would have pi over 4 plus 2 pi n over 3, right? Over here, if you divide by 3, it's basically the same thing as multiplying by a third. So you'll have 5 pi over 12 plus 2 pi n over 3. And so, like, for example, this is, 45 or pi over 4. And before, we would have just had a normal plus 2 pi n, and we would never get another solution in one lap. But now, like, if n is equal to 1, if you add 120, or 2 pi over 3 to pi over 4, you're going to get another solution in one lap. So you really have to be careful in this one. That's why this one's trickier, of these kind of orange 2 pi over n's. They are going to become more important even though you're doing one full lap. Like when you divide the lap into thirds, you can get more solutions, basically. So like over here, you're going to have a solution at pi over 4, but then you could also have pi over 4 plus 2 pi over 3. And if you do that, you'll have, 11 pi over 12? Yeah, you do common denominators, right? And so then, let's think in degrees here for a second. So we basically had a solution at 45, and then we added 120, right? So that's 165. And if we try to add another 120, that's 285. So that should also be a solution we should include here. So pi over 4 plus 2 pi over 3 times and double it, right? That's basically another solution. And if you simplify that one, you're going to get 19, you're going to get 19 pi over 12, okay? But if you take your 19 pi over 12 is 285, and if you add 120 to that, you're at 405, and so you're beyond the 2 pi you want to be at. So that's all we're going to get for the first one. And then for the second one, right, definitely get a 5 pi over 12, right? We got that. That's like, where n is 0. And then same kind of thing, we could do 5 pi plus 12 plus a 2 pi over 3. And if we think in degrees, because again, maybe it's easier, this is 75. 75 plus 120 is 195, so this should definitely be included, right? That's an answer in one lap of the circle. If you do common denominators and stuff there, right, this one's a little nicer because you can just get a common denominator of 12. So you just multiply that by 4, so that's 8. 8 plus 5, 9, 10, 11, 12, 13. Still counting on my hands. 13 pi over 12. So this is 13 pi over 12. And then, again, we want 5 pi over 12, and then we're going to plus 2 pi over 3 times 2, right? So if we're thinking in degrees, because it is a little easier here, 75 plus a 120 was 195, plus another 120 is 315. So that should also be in one full lap here. And 315 is actually a nice one, right? That's 45 degrees less than 2 pi, right, or 360. And so this is actually 7 pi over 4. That's just kind of a nice one. But you could just get common denominators to get the answer. But it is just 7 pi over 4. And there's no way you could get another one, because if you added 120 to 315, you're going to be at 435. And so that's beyond the 360 degrees that you're allowed to work with. So pretty tricky problem. I think it's pretty straightforward to get 2 solutions there, but to get the other 4 is kind of weird. And you just basically have to remember that there kind of is always this 2 pi n, and then we're dividing by 3, right? To get different increments of that. So yeah, that one's kind of tricky. All right, so this one, a little more straightforward. So it just says find all the exact solutions to this thing on one lap, for the equation secant x times sine x minus 2 sine x equals 0. And anytime I see in math, 2 terms with a common factor, my brain just thinks like, take that out, right? So take out a sine x, and I'd have secant x minus 2 left over. And then you kind of get naturally 2 problems from this, right? One of them is when is sine of x equal to 0, and one is when is secant x minus 2 equal to 0, or just secant x equal to 2. And really, you could just take the reciprocal of both sides here, right? 1 over secant is cosine, and 1 over 2 is a half, right? So now we've gotten it down to a point where we can kind of just think unit circle stuff. So, for sine equal to 0, I'm basically thinking when is the y value in the unit circle equal to 0? The y value, as you go around equal to 0, happens basically just at the x-axis, so 0 and pi, right? So 0 and pi are solutions for that part. And then for this, you just need to use finger trick. Cosine of x equals a half. You're thinking square root of fingers above, and that needs to equal 1. So you've got a reference angle of a pi over 3. And if you think your acronym, you can't be here because sine's positive. You can't be here because tangent's positive. So basically, you've got a pi over 3 in, sorry, I wrote a 6. A pi over 3 in reference angle in both quadrants 1 and 4. And so one of them is just literally pi over 3, right? That's the first one. And then to get this one, I'm just thinking honestly, to go around is 12 pi over, 6 pi over 3, right? 6 divided by 3 is 2. And so going 1 back is 5. So this is 5 pi over 3. That's kind of how I think of that one. Okay. Any of these solutions could work. And you just want to think, about domain always in any equation too. And I didn't actually talk about that in the last problem, and I should have actually, to be honest, but you want to make sure that, because you really do have a 1 over a cosine right in here, so you've got a rational function. This is a rational function, right? you want to make sure that your rational function is well defined everywhere. And, certainly these are not going to give you cosine equals 0 on the bottom, because we just solved cosine equal to 1/2. And also over here, where sine is equal to 0 is not where cosine equals 0. So 0 and pi are not going to be an issue basically here also. So it is important to kind of make note of that, but it isn't a problem in this example. And the domain actually isn't an issue in this problem also, because there is no division by 0, which is really why I didn't talk about it. But you don't have a rational function, right? You don't have like a 1 over cosine or something like that. All right, just a few more. So similar kind of thing, very similar actually. We want all the solutions, 0 to 2 pi of tangent x minus 2 sine x times tangent x equals 0. So very, very similar. I have a tangent in both terms. Take that out. I'd have a 1 minus 2 sine x left over, right? You get two problems. You get tangent of x equals 0, or 1 minus 2 sine x equals 0. I'm just going to work with this one on the right for a second. This is the same as 1 equals 2 sine x, or 1/2 is sine x, right? Go to unit circle stuff. Tangent is equal to 0 when sine is equal to 0, right? Because tangent is just sine over cosine. So honestly, this becomes the question, when is sine equal to 0? And we literally just did that in the last problem. It was 0 and pi. And then this, very similar to the last problem too, we want to know when is sine of x equal to 1/2. So now we're thinking square root of fingers below over 2. And you can kind of see that has to be like a pi over 6 or like a ring finger kind of thing. And so you basically are getting these little 30 degrees, and it's in quadrants 1. All students take calc. It can't be here and it can't be here. It's in quadrants 1 and 2, because that's where sine is positive. So you're getting a pi over 6, definitely. And then, that's this one. And then if you go, if you had went to halfway, right, that would be 6 pi over 6. But we're going back 1, right? So we're going 5 pi over 6. And same kind of thing, I was talking about the domain. You have tangents, which are sine over cosines, and you want to make sure that your answers are not when cosine equals 0, because if cosine equals 0, then it's going to be undefined. And none of these, right, are where cosine equals 0. Cosine only equals 0, like on the y-axis. So, pi over 2 or 3 pi over 2 are multiples of those. So those 4 solutions are actually solutions. All right. This one's a little different. Still an equation, so we still want to find all solutions from 0 to 2 pi for sine squared minus cosine squared minus sine of x equals 0. And what I'm thinking about here, it's never great to mix trig functions in the same equation, so it's kind of a good thing to try to get this to be one function. So what I might do is switch cosine squared out for a sine, right? Because I know that sine squared x plus cosine squared x is equal to 1, so cosine squared x is 1 minus sine squared x. And that's going to be kind of what I use first. So I'm going to use this. So I have sine squared in the problem minus, and then I'm just going to pop in this, 1 minus sine squared. That's my cosine squared. And then I have just minus sine x equals 0. Let's just simplify a little bit. Combine some like terms. And then it turns into one of these like quadratic trig functions. So I'm going to use u sub. I'm going to let u equal sine of x, okay? And if I do that, then I'm really just solving a quadratic 2u squared minus u minus 1. And I think this factors pretty nicely here. So I want to get minus u in the middle, so that should probably be negative and that should be positive. So u is negative a half, u is 1, right? And then you just unsubstitute, right? Like using this, u is sine, so I'm basically solving when is sine of x equal to negative a half, and when is sine of x equal to 1. Go over to your unit circle, kind of same old stuff here. I think we just solved one of the, oh no, we solved sine of x equals a half, so. But same reason why this reference angle is pi over 6. We basically still have a pi over 6, but we're in different quadrants, right? Before we were in the first two, but now we don't want to be in those because it's negative. We want to be down here. And so for this one, right, we would get x equal to 7 pi over 6 in quadrant 3, and then 11 pi over 6 in quadrant 4. And then for this, you're thinking, when is the y value in the unit circle equal to 1, which just pops you up right there. That's the only place you have a y value of 1. So, so basically, you could get pi over 2. No need to worry about domain. You have no division by, have no rational functions, right? That's the easiest way to say it. Everything is on the top line in the numerator, right? Nothing in the denominator. So really no need to worry about that. Just go ahead and circle answers or whatever. All right, just one more. So for this one, it uses like a double angle thing. So the question is, find all the exact solutions on 0 to 2 pi, or state the equation does not have a solution for the equation sine squared x minus 1 plus 5 cosine 2x minus cosine squared equals 9. Whew. So, we already have some like terms we could combine if we wanted. We could add 1, right, over, and we get sine squared x plus 5 cosine 2x minus cosine squared equals 10. Cosine 2x, one of the trig identities is, we'll just do it like this. I used this before in the first problem, cosine squared minus sine squared, right? And then if you distribute the 5 in, I'm just doing this because then I could combine some more like terms, right? So I'm going to actually do a few things at once here. So 5 cosine squared minus a cosine squared is a total of 4 cosine squareds, right? And then sine squared, and then minus 5, right, sine squareds is minus 4 sine squared. And then probably what I'm going to do, I'm just going to divide by 2 because everything's nice divisible by 2. And then, we have a cosine squared and a sine squared. I can simplify that even more if I use, the Pythagorean identity. So basically, since again, sine squared x plus cosine squared x equals 1, right? Let's take the sine squared out. So sine squared x will equal 1 minus cosine squared x, right? So I'm going to use that in here, right? So I have 2 cosine squared x minus, right? Minus 2. And then sine squared is 1 minus cosine squared x and then this all equals 5. And so I have, if I simplify that, what colors do I want to use? We'll go here. 2 cosine squared x. I'm just going to distribute minus 2 plus 2 cosine squared x equals 5. So you have 4 cosine squared x's. If you add the 2 to the other side, you get 7. So now you can go ahead and divide by 4. And then if you think about what numbers squared to 7 over 4, it would be plus or minus the square root of 7 over 4, or square root of 7 over 2, right, is the square root of 4. And finally, you can see what's going on here. So cosine of x is equal to plus or minus square root of 7 over 2. You know, square root of 4 is 2. 7 is bigger than 4, right? So this number has to be more than 1. And, you know, cosine of x is always greater than or equal to -1 and less than or equal to 1. So this makes no sense. You can't have something like cosine of x equaling basically a number greater than 1 or less than 1, right? And that's what we have happening here. So long story short, there can't be a solution to this problem. There is no solution because you get down to an impossible equation like that. So that one's also a little tricky, a little weird, but good one to kind of see worked out.